we're going to take a look at what happens when an object moves in an airflow. And the standard explanation of this is Bernoulli's principle. What we've got here is a hose connected to a blower. This could be the exit tube of a vacuum cleaner. What we're using here is a blower from an air track. So air is going to flow out of here. Right now there's no air flowing and my ping pong ball just sits there. But when we turn the air on, we've now got a column of air coming out of this tube. And if we're any good at this, we can get the ping pong ball to levitate. Now, the stability is an interesting thing. Certainly the air could blow it up, it would go up, and it would just keep going. We clearly have a case of kind of a terminal velocity in that it's risen to a height where the air hitting the bottom of it is delivering the same force as gravity is delivering. But why does it stay balanced on that column? You can see it tries to go sideways, but for some reason comes back to the center. So there's a centering force. And that centering force is based on Bernoulli's principle. If you visualize a column of air here, if the ball tries to move out of the column of air, it moves to a region where the outer edge of the ball is in still air. And so one half of the ball has high velocity air going past it, the other half of the ball has stationary air. According to Bernoulli, the pressure of fast-moving air is lower than the pressure of slow-moving air. And so as it tries to move off-center, there is a low pressure towards the center that pulls the ball back in. Now you say, all right, sounds like a good story, but I could believe it would just sit there based on the balance between gravity and air pressure. So, as with any decent science, this really has to stand up to observation. So what if we don't have a vertical array? What if this thing tilts and we're relying entirely on air velocity? And so I'm going to tilt this over, and please note now, the ball is no longer directly above the nozzle. It's hanging over nothing, which means there must be something going on with trying to exit the airflow. And it doesn't matter whether the airflow is vertical or not. As you can see, eventually we get some stability issues if we push it to its limit. But the faster the airflow and the heavier the ball, the more stable it will be. In other words, the question really is, what are the combination of forces acting here? And a ping pong ball is awfully light, so just a little air turbulence is going to make it pick all sorts of other options. But once again, this is repeatable behavior, and we've now got this ball out there in space, not directly above its airflow.
You have faster air above the ball and slower air below the ball.
Right, so when the ball tries to drop out, it moves into a slow zone, and the fast zone puts a lower pressure, and that low pressure exceeds the ball's weight and pulls it back in.
But you imagine the steam lines coming out of here and spreading out. The steam lines spread out. So then you get fast air and maybe directly in front, and then as you get farther out.
Yes, exactly. Yeah, it's not an on-off switch, it's a gradual field. It's very hard to get it to stabilize off-center. And so in general, we stabilize here, and then once it's found some equilibrium, we sneak it over here, and it doesn't know what we did to it. And we're out there in a region that's not directly above the source of the airflow. To revisit the stability of the ball in the airflow based on some updated thinking, these days it's been realized that Bernoulli's principle is the equation is a conservation of energy equation. It works fine inside a closed tube. When you talk about airplane wings and baseballs, they're in an open system, and the conservation of energy is a harder thing to keep track of. Here at Penn, we had a high-energy particle physicist named Howard Brody, whose hobby, and more than hobby, his avocation was tennis. And he began to direct his physics skills at tennis and ended up becoming the premier authority on the physics of tennis in the world. And Dr. Brody was an advocate of this approach long before it became popular in the journals and the textbooks. Today, this is referred to as the Coandă effect. And the Coandă effect suggests that the effect of a fluid on a moving object is not so much based in an open system, like, so we're talking a baseball or an airplane wing. It's not so much a Bernoulli problem as it is a conservation of momentum problem. And what Dr. Brody used to say about tennis balls is that if you wanted to know where the ball was going to go, you said, where is the air going? So as the ball moves through the air, the question is, how does it dump the air that's in front of it? The air comes past, and if that air goes around the ball equally in all directions, then the ball goes straight. But if the ball's got some spin on it, it's going to have a preferred direction. And the term Coandă relates to the fact that fluids tend to cling to surfaces as they go past them. And so it turns out that this fluid going past the ball is going to cling to the ball and not let go in a straight line. It's going to curve and go off at an angle. And this is clearly what happens with an airplane wing. And so now we say, all right, we had air moving horizontally as it arrived. We have air moving with an upward component as it leaves. So if the air received an upward component of momentum, the ball, in order for momentum to be conserved, is going to get a downward component of momentum. Now, once again, we would like to illustrate this, and one of the better ways to do it, and I apologize for the fact that on video this is not as clear as it would be if you do this in your own kitchen. Just get yourself a fairly large serving spoon that you can hang from a free hanging point. And if you put this in the sink and run water vertically down on the back of the spoon, you will note that the water hitting the back of the spoon, and your first thought would be, if I have the mass of water hitting the back of the spoon, it would probably make the spoon move away from the water. But what you're going to watch happen is that the water clings to the spoon, wraps around, and exits, moving towards the scoop of the spoon, away from the bulge. And so we're going to do that. I'm going to place the spoon here. You can see the silhouette, and we don't have a spigot, but I've got a bottle of water. And so we're going to run this water down vertically. And you note that when the water hits, the spoon surges toward me. And you can see the water leaving the spoon in a direction away from me, because of this clinging effect. And of course, this is what happens with an airplane wing. As an airplane wing moves through the air goes over the wing and comes down that curve, goes downward, which gives the wing a comparable momentum upward. And so this is the approach that is generally used these days as an explanation for the lift of an airplane wing or the curve of a curveball as it flies through space. So what we have here is a column of water. We had to give it some color. It's a column of water. The red tape is covering 3 holes in the side of this column. And so what we're interested in is the effect of height on a fluid column. Bernoulli's principle is actually an equation, and it's hiding back there on the blackboard. As we have alluded to, it's a conservation of energy equation, and it essentially says that you can slosh things back and forth between pressure, height, and velocity. And if you notice, the combination of those 3 variables, if managed with the right math, is going to be a constant. And so what we're suggesting is that height makes a difference here. And if we don't have a velocity, if the third term there has a 0v, this reduces to a pressure-height relationship. And it turns out that the pressure is going to be proportional to the height. In other words, we've got a constant with P and H being involved in its calculation. You have experienced this. If you go to the bottom of a swimming pool that's pretty tall or pretty deep, you notice your ears popping. There's a real issue there that the water starts to weigh enough that it's putting pressure on your eardrums, and your ears are a pretty sensitive pressure sensor. So we've got a stack of water, and the water ends up pushing down, and the more water above you, the more it pushes. And so you're going to have a second atmosphere of pressure on your ears at 10 meters or 34 feet down. Well, it turns out that we think that the pressure of this water is not very heavy right here, and that it gets more pressure in the middle and even more down at the bottom. So what I'm going to do is peel this tape up, and we're going to look at what does this water do. Well, what it does, if we look at our Bernoulli equation, we're now going to bring velocity into the picture. And if we've got more height, then we've got water that when we give up that height, we'll get more velocity. And so the water down here is going to come out, and the interesting thing is, if you sit down and work out the numbers, the velocity that the water will exit the opening down here is the same as the velocity that a stone would have if we dropped it from the top of the water, because it's all gravitational potential energy, whether we're using it with water down here or with a falling stone. And so clearly, if the stone falls less distance, it would pick up less velocity. We will see the velocity manifest as the distance that the arc travels before it runs into the ground there. So we'll add a little water to make up for what's leaking here. And if I'm any good, I'm going to peel this tape up. And we can clearly see that the water at the bottom had the greatest range, and the water in the middle, and the stuff up top, we passed that opening pretty quickly, but it didn't come out very rapidly at all.
And by analogy with projectile motion, the range of that parabola lets you infer the initial velocity that comes out.
Correct. We have a hose coming here that we're going to be able to blow air through, and we have a glass tube here which has been necked down in the middle. And you can kind of see that it's got a dimple there, so the cross-section of it has been reduced by at least a factor of 2. So the air will come in a wide section of glass right here. It will pass through a narrow section and then continue out through a wide section. If you've been paying attention to Bernoulli's equation, you can see it on the blackboard there behind us. You note that there is a velocity term near the equal sign and a pressure term. You will also note, and it's not accidental, that we have set this up horizontally. And setting it up horizontally, we have removed the H term. In other words, what goes on in any place here has the same height as what goes on in any other place. And so we're really going to look at the relationship between the pressure of the air and the velocity of the air. And so the equation of continuity tells us quite simply, okay, if we've got a big cross-section, we can move a lot of volume without going very fast. But if we get a narrow cross-section, like the rapids in a stream, and what happens at the rapids? The water runs fast because it's not deep. And suddenly the cross-section disappears and we got to go very quickly. Because remember, no molecules get in at the entrance unless some molecules leave at the exit. And so to get these guys some room to come in, these guys have to find a way out. And so we can then say that we've got a low velocity in this wide opening, a high velocity here, and a low velocity here. Now down here we've got 3 connected tubes. They've got water in them, and right now the height of that water is determined entirely by gravitational potential energy. And not surprising, each of these guys has chosen the same height, because if any one of them were higher than the other, the gravitational potential energy would have pushed these guys up, they would have come down, and bingo, we're back to balanced. But each of them opens into a separate section of the tube. And so we have suggested that according to Bernoulli, high speeds here lead to low pressures. Low speeds here and here are going to lead to higher pressures. And so we think, if this assumption of the Bernoulli equations is true, that if we run air through this, we are no longer going to have equal levels of fluid, but rather we're going to see the fluid in the center tube go up to react to the lower pressure it senses at the narrow section of the pipe. And so over here I've got a compressor, and the compressor is going to feed air through this tube, and we're going to see what happens. And so here we go, and look, I'm out of the air is moving through the tube this way. So the pressure is on this side, it moves through and exits on the open side of the tube. And so here we go. And as soon as we lower the flow rate, we're back to just a steady state of fluids seeking their own level. But if the air moves at a high rate of speed, we can actually get that fluid to move to a pretty good height. If we pump up the pressure in that compressor, we can actually get this to come so high up here that it gets caught in the airstream and gets blown out. What we have is an atomizer. And this is the way a perfume atomizer works. That you take a bulb, you've got a little container of perfume, there's a tube running across the top, you squeeze the air, the high-speed air draws perfume up, and the perfume gets blown out the side. This is also the way that archaic device of the internal combustion engine, the carburetor, works. Because in that, we draw in the air that the engine's going to use past a tube that goes to a reservoir of gasoline. And again, the low pressure draws the fluid up, and if we design it right, we mix the gasoline, one part of gasoline, to about 15 or 16 parts of air, and bingo, it burns nicely in your engine. Not as well mixed and organized as if we use a fuel injector. And so the carburetor is no longer used these days because we care about both mileage and emissions. But cars built up until the 70s or 80s all had Venturi devices, and that's what this tube is called. It's a Venturi tube that relies on Bernoulli's principle to draw fluids into a low pressure area.
Well, what we're doing here is we're using this tiny, roughly 4 centimeter pressure head as a source of, so basically you have density of water times little g times height is the difference in pressure between this water and the atmosphere. So we have a so-called 4 centimeter pressure head, so rho gh. That's going to be a pressure difference. And the flow rate, if it's laminar flow, should be proportional to that pressure difference between here and here. So this is going to be density of water times little g times 0.04 meters. This is going to be atmosphere, so that's delta P. And then it's times the radius to the 4th power of this tube. So this is a tube with a 1.9 millimeter diameter. When we have another tube that has a 1.0 millimeter diameter, so it's roughly a factor of 2 in radius. So this is the high radius tube. This is going to be the low radius tube. So we expect to get roughly 16 times as much flow out of the big tube as out of the little tube. They're the same length. Now downstairs in the denominator, you have the length of the tube. In the denominator, you also have the viscosity of the water. But it's water in both cases. It's the same length. So the only thing that's going to change here is the radius. So our claim is that by changing the radius by about a factor of 2, we're hoping to see in Poiseuille's law that we're changing the flow rate by roughly a factor of 16. It's not exactly a factor of 2, so it's not going to be exactly a factor of 16, but we're going to see if we're in the right neighborhood. So we are using a scale here to measure grams of water that we collect, and then we're recording the data with a computer. The computer's going to measure the slope. It's going to tell us the flow rate. Now we really want cubic meters per second for SI units. This is going to tell us grams per second, and we're going to divide out the density of water, and we're going to put it into SI units, and we'll get some extremely small number of cubic meters per second. Okay, so here we go. Okay, are you ready? Okay, so we're going. This is about the fastest we can go for it to stay laminar.
Right. And the other one's even slower. It's laminar in the tube. It's dripping because it's got to build up to a drop that weighs more than the cohesion.
Okay, so we can measure the slope and then put on the smaller diameter tube. Let me just zoom in for a sec. Okay, so that was the result. Yep, oh yeah. 0.4364 grams per second.
And this next one will be low, right?
Oh, it's going to be a lot lower.
Here it's running.
It's running? Okay, here we go. Here we go. Yeah, it drips so slowly. Okay, those are very different slopes.
0.04028.
10.8, and our prediction is 10.2. I would say that's pretty darn good.
Wow.
Nice. Okay, cool. I think that's pretty neat.
That's as good results as I've seen.
Yeah.
And I think your Reynolds number calculations are critical. We got a piece of truck inner tube stretched across a trash can, and I can hit it. I'm not going to get a job in the Philadelphia Orchestra with this. If you take a look at the trash can, here it is. It's just a great big Rubbermaid monster trash can. But if we swing it around here, So what's happening? We could model this in many ways, but it kind of seems as if we're getting air to come out of this hole and to come over here and move these styrofoam cups. You know, sounds good, but if we're going to do decent science, we ought to be able to experiment with this. This is a model that could be tested. Our problem is we can't see air unless we tag the air with maybe smoke. So let's do that. So there's some smoke.
I almost don't reach.
So instead of having the smoke outside of the drum, we're going to put the smoke inside the drum. And let's just see what happens first. Oh, is that cool? So we were right. There's a plug of air moving when I hit this. So here's my hammer, and I'm beating the drum back here. And that plug of air is better organized than you thought, isn't it? What if we shoot it right at you? Are you paying attention now? Oh, that's pretty cool. Here's a plastic bag. We can see where our projectile goes. Ooh. So this really is a neat thing in that you kind of thought of air as a continuous quantity, but this is a discrete lump of it that seems to be moving. So let's go back to the cups briefly and see if we can observe this happen with our projectile made apparent. And ooh. So notice what's coming out of here. What's coming out of here isn't just a random lump of smoke. Look at that guy right there. Ooh.
At low speed, it's really impressive.
Yes, and so look at those babies. You can blow smoke rings without getting lung cancer. This is a major breakthrough. And so those rings are something called a vortex. And what's happening is we're firing air. We're compressing the air in here. It's coming out through this tube. And because it has to pass the opening of the tube, there's a speed difference between what's down in the center and what's out near the edge. And that means that the center stuff is moving faster and we get a rotation. We get a vortex. There's a ring of air that is different than the air around it. And that's our plug of air. That's our vortex. And it's forced out, and because of its rotation, it maintains its stability.
Are there any familiar examples of vortices when you look up at the sky?
Most particularly when airplanes are flying in the upper atmosphere. They are leaving what's called a contrail behind them, and that is a trail of vortices. And what's going on there is the gases from the engine exhaust and the pressure change is causing condensation of water to give you smoke just like this that lets you see the vortex. And that trail runs along behind the airplane. Conditions have to be just right, but on a bright sunny day you may look up and see that white line of cloud following behind a jet plane. Used to be when you drove down City Avenue in Philadelphia, they had steam pipes running under the road, and in the winter there would be steam coming off of the road, and you'd see vortices behind the cars as they moved down the road. Vortices occur in many places and are critically important to understanding the behavior of aerodynamics in everything from meteorology to designing airplanes. So this plug of air, we earlier spoke about the behavior of fluids moving past objects. So we've got two cups that are separated, and now you're all believers that we're sending a plug of air out, and if we aim correctly, we can get that plug of air to move through here. So we spoke earlier about that Bernoulli effect that said that fast fluids have a lower pressure than slow fluids. So there's going to be a moment when there's a fast fluid moving through here and a slow fluid over here, which means the pressure is going to go down in the middle. Your first reflex would be to say, well, if I run something through here, it's going to push these guys apart. And so we're going to see, does the Bernoulli effect overcome the simple getting out of the way problem? So let's see how well I've aimed this.
Oh.
Okay, and so now we're drawing them together because we're shooting right down the middle. So let's set that up again. It seems like we've got it aimed well. And so we do seem to be able, but if I hit one straight on, we knock it off. There, that was kind of a dramatic one, and they bounce off each other. So this is kind of a neat tool because once we tag the air and we get the smoke showing, we can actually see where the moving air is and take a look at how it influences things around it. Wow.
That's beautiful. Do it again.
Yeah, I think we do better with just white light here, huh?
Yeah.
It's almost like you could box these things and sell them.
One thing I'm not sure is obvious on the camera is the spinning motion of the vortex.
Okay.
That's cool. Yeah, I like to be able to see, you can see the spinning of the vortex. I think it's also cool if you're going right at the camera and you see it spinning.
Yeah, do it again.
Point of view.
Yeah, do another one.
Oh, okay, this is your flat plane. Okay, so what do we...
I see. I thought you might want to catch the plane perpendicular to me.
Right, but you'd have to scan pretty quickly. But I'll tell you, that dot moves.
It's too big to be.
What? That is actually really cool looking though.
Yeah, poof! Okay, yeah, there, okay, that's good.
I'll be right back. I'm going to go get my phone because I want to catch this.
Okay, then another. Try the rings now.
Yeah, and see, that shows up. Now what?
Let's try that. That's kind of cool.
Yeah, it is.
You kind of see it travel along.
Yeah. Oh, I tell you, it's really cool looking from my viewpoint.
Yeah.
It looks like a hockey puck running out to Bill.
Which kind of negates the effect that we want them to see.
Right, because we don't get the vortex, we just get the...
I almost feel like we need something that will disperse the laser in both directions.
Well, you know, the old, those laser projection things where you have the mirror that's oscillating.
Yeah.
So you almost get a video sweep. So the laser, in essence, fills the space faster than the eye, you know, in less than a 30th of a second.
Yeah.
So then you could shoot your smoke across it.
What
And
about if we just rotated another one of these apertures onto that?
yeah, I was thinking of a diffraction grating, but this is more like a, I mean, they've done this so you don't really see, yeah, what diffraction orders. You just see one full smear. It's almost like a barrel lens. See, there you go.
Oh.
Because looking along the lines of the light really...
Oh, that's great.
Try to walk over a little more, and let's see whether...
Oh, now if you're aiming toward the camera, that's maybe even a better effect.
See, the sight lines, when you look into the light, you get the strongest image of what the laser is doing in the smoke.
Yeah, actually, Mary, maybe if the direct light from the laser is going a little bit away from the camera.
Like that?
Yeah, or like if you stand closer to the camera and aim the laser a little toward the source.
What do we get there?
So you want me to stand by the camera and aim towards Bill?
Ooh,
That's a good.
yeah. So we almost need to just get an eclipse device, you know? Oh man, look, some of that's really good stuff. Wow. Oh, look at those secondaries.
Yeah, I wonder what explains the secondary.
I think it's echoing. You know, I think it bounces off the front, comes to the back, and we get a second ripple.
It's a pretty long time. Yeah.
Yeah, but this is clearly not moving at the speed of sound.
Right, it's the speed of the air movement.
Yeah.
That makes sense, actually. Yeah, it seems compatible with the time it would take the vortex to cross the tube.
Right.
Yeah.
Yeah, that.
Pretty cool.
Wow. Look at these guys. Oh man. 3. I mean, this is just sloshing around like a bathtub.
Sloshing is probably the right word for that mode. Yeah.
Yeah, and when you hit it hard, you have so much crap going on, you can't see the secondaries. That's really cool.
Yeah. Oh, now before you hit that too hard, let's see if we can make it really. Oh, I know.
Oh, that's nice.
That's pretty good.
Yeah.
You don't need a marker really to show the puck's moving because you can see the
Yeah,
needle.
it's in the frame. Projectile. I mean,
Right here, you just see it splash through the plane.
right, like you don't get any sense of momentum there. See, whereas here, look at that.
Oh, that's kind of cool.
That is.
Try slowly. Oh, I can make them perpendicular.
Whoa.
Oh, that's pretty cool.
Yeah, here, look at these 4.
Wow. That's gorgeous.
Isn't that something?
That's like, have fun.
Wow.
Beautiful. Do it again.
Yeah, I mean, I think we do better with just white light here, huh?
Yeah.
It's almost like you could box these things and sell them.
One thing I'm not sure is obvious on the camera is the spinning motion of the vortex.
Right, and see, I would almost think you want to bring a camera right down here.
Yeah. Harbor Freight.
Okay.
That's cool. Yeah, I like to be able to see, you can see the spinning of the vortex. I think it's also cool if you're going right at the camera and you see it spinning.
Right, I mean, Mary may have
Yeah, do it again.
the point of view.
Okay, so I got 2 videos here that might be worth it. So I'll get out of the way.
Yeah, some of these, boy, you really get like
Yeah.
outer and inner surface detail.
Yeah. Yeah, kind of ghost-like. Oh, now look at that. Oh!
Wow.
That's cool. You can really see the vortices.
You've got some rotation.
Yeah.
Alright, so I don't know if that actually airdropped to you, so I'm also going to text.
Oh, I see.
If you go this way.
I love that there's a text group in my phone called Bill and Bill.
Bill and Bill. Bills.
Can we,
Right, it's a question of like, how do you get enough light on the smoke without having too much light in the camera?
yeah.
That's cool.
Oh, was it that one?
I think this machine is described in the Feynman Lectures, the second fluids chapter.
Really? In what, in fluids, you said?
I think he gives dry water and then wet water. I think it's his wet water chapter.
Uh-huh.
Let me try it this way. Okay, slow-mo one isn't working, so hopefully it airdropped to you.
Oh, slow-mo, cool.
Yeah, so this is the slow-mo one, and I feel like the very first one in slow-mo is like here.
Nice, yeah.
Once the slow-mo kicks in. Oh, did I have fun? Oh, that's what makes it for. Oh, here we go. Here's another one slow-mo.
Oh, yeah. Oh, wow. Yeah, that's cool.